What's up, folks? On today's episode, we're talking about cell antennas. And I'm not talking about cellular like your phone. I'm talking about cells inside your body, the little microscopic cells. We're learning what communication methods cells have with one another, what the secrets there are behind that. And we're able to spy on cells now and hopefully start to crack the code on diseases like arrhythmia and Alzheimer's. Hey everyone, like we mentioned today, we've got a really cool article for you guys talking about how we can use light to crack the code of how cells are talking to each other. Not cells meaning cell phones, but cells.
Which is definitely what I thought at the beginning.
Yeah,
I'm gonna be honest.
I know. But cells, like the little tiny units of life inside your body. But before we get too flushed away with that, I want to mention today's sponsor, Mouser Electronics. As you may know, Mouser is one of the largest electronics distributors in the world. As a result of their massive foothold in the electronics market, they've got an awesome finger on the pulse of what trends are going on in technology, and they write awesome articles about it, which we get excited to share with you guys because that's what we're all about, is sharing awesome technology that's on the forefront and letting people know what's coming before it happens. Mouser does a great job of doing that, and we've got one linked in the show notes today. Called Stop Flushing Away Your Health Insights, and it's about smart toilets, and not just smart toilets in terms of like having a lot of bells and whistles like a warmed seat or electronic bidet or an automatic lid that flips up and down or automatic flushing. Like all those things are cool, but they're talking about smart toilets in terms of turning your toilet into a health device, which is an interesting premise. And I've actually this article was published in February 2024, so almost a year ago. Talks a lot about all the different potential applications, what makes a toilet smart, what are the potential impacts it could have. They even mentioned challenges to adoption, right? Like no one wants to have a bunch of sensors on their toilet. Makes you, it's a pretty private part of life.
But invasive as it could be,
it's just about as invasive as you could be. Like, I don't want people looking at me while I'm in the toilet. Like,
yeah,
this almost certainly would involve small cameras. So they talk about, the gamut of this potential adoption, et cetera. But they also kind of have already preceded their time a little bit, right? So this was published in February 2024. I recently heard about a startup coming out of stealth called Throne Science. And this is exactly what they're doing. And Throne Science is, we talked about this a little, it's like a $300 smart toilet seat that's supposed to capture your hydration levels, that's supposed to look at your number one and your number two to tell you how you're doing and monitor your health, which is a really, really interesting premise. And it just goes to say, Mouser was ahead of the curve on this one. So when we tell you to check out one of their technical resources saying that it might predict the future, we're onto something.
This is the third or fourth episode we've done where the ad has predicted the thing we're about to talk about. So I would say they're pretty spot on.
Yeah. All right. So we've got that linked in the show notes. Check it out if you're interested. Now we're going to get back to very similar but also very different realm in terms of health, in terms of technology, but spying on cells, right? So I've alluded to this a little bit, but we've got these, I guess cells in general, that the premise here is cells send electrical signals between each other to communicate. And scientists have long believed that understanding these signals can help us crack the code behind diseases like arrhythmia, which is irregular heartbeats, and things like Alzheimer's. And the way that cells communicate with each other is with neuron signals that are about the size of 100 millivolts. So they're very, very small electrical signals, and that's how cells are communicating with each other. That's how a lot of these diseases, or they think, the hypothesis is, how do we crack the code behind these diseases? It may be by studying these electrical signals, but the current devices use wires, which limits how much data can be collected. The thickness of a wire is going to be much thicker than a cell, right? And you would need a ton of wires to be able to capture an area of cells. So you're
just doesn't
physically
scale,
limited.
yeah.
It doesn't scale well. Yeah. And so because of wires being the physical limitation on how much data we can collect, we haven't really cracked the code on arrhythmia, and we haven't cured Alzheimer's. But there's this team from MIT that's created a wireless method, tiny wireless antennas they call oceans is the acronym.
I would give it easy 8.5 out of 10, by the way. Very solid.
Well, and when I first looked at this, I'm like, okay, oceans, how does this relate to cells? But I think when we describe the sensing mechanism here, we'll get really, really, get really, really close and explain why Forbode thinks this is an 8.5 out of 10 acronym here. They're able to measure changes in electrical signals in liquid, and they use light scattering to detect these signals, essentially replacing the need for wires, and we can use light as the medium for communicating or capturing these electrical signals. And it's really, really interesting. They've got this special material that changes its shape. It changes how it scatters light when there are really, really small electrical signals nearby. And it's a very, very sensitive, the way I like to think about it is like a funhouse mirror, a very sensitive funhouse mirror that changes shapes when it detects tiny electrical signals. And so when you shine light on it, you can detect how the shape of the material is changing. It's getting all wavy in response to electrical signals, which is why oceans makes a ton of sense. When it gets all wavy in response to electrical signals, you're able to use light and changes in the way that light is scattering off of these oceans sensors to track movement of ions in liquid, which is how these cells are communicating with one another.
Yeah, I mean, you mentioned the approach that doesn't work is the wired one, like when you have a physical connection. Well, these are technically wireless sensors. They call them like antennas. And like you're saying, the mechanism by which they send information back is whenever the electrical conductivity around them changes, they change as a result and they reflect light differently. So every time the liquid around them is charged, they change in a way that the intensity of the light they're reflecting back increases, so they get brighter. And every time it decreases, it becomes more and more diminished until it's pretty much dim. What's cool about this is these antennas are composed of a conductive polymer called PDOT with another layer of a different polymer that allows them to change the shape called PSS. But what was fun is earlier on when they were doing this research, they added gold nanoparticles as a way of reflecting that light and getting that conductivity changed. And then they realized that the gold wasn't even necessary. So the thing that was giving them that behavior was the PDOT. So that in itself was like a very exciting breakthrough, which is kind of like buried in the midst of everything else that they got going on here. But for the material science folks out there, I figured they might appreciate the little shout out.
Yeah. And so I think two things we want to touch here to make this abundantly clear. Mm-hmm. Right. One of them is the manufacturing method. You kind of alluded to it a little bit. They've got these thin layers, one of them being PDOT, the other one being PSS, on top of a glass base. And essentially they use this glass base. It's covered with these thin conductive layers. And then tiny holes are etched into the layers using a focused ion beam. Like imagine a really, 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 really narrow laser beam for cutting.
I think they called it a nanoscale pencil. That's what the researchers called it.
I love it. Like it's just etching tiny holes into these layers, and then they add this special liquid PDOT PSS solution, and they can grow antennas in these tiny holes
that grow,
like a little tiny mushroom on this farm, so to speak, that they've cut a bunch of holes. Yeah. The sensing mechanism here, I want to highlight that too. Mm-hmm. So cells are already sending tiny electrical messages to one another. Somewhere in the order of 100 millivolts is the size of these electric signals that they send to one another. And that creates ionized particles in the liquid around them, and it causes those ionized particles to move. So that's a phenomenon that already exists inside every human body. These are how cells are communicating to each other with many electrical signals that we actually don't know much about yet. Sensors haven't been able to capture those effectively so far, but this new sensor reacts to these messages that cells are sending to each other by changing its shape, by changing how it reflects light backwards. Like I like to say, like a funhouse mirror. Like, you know, when you look at a funhouse mirror, the shape gets distorted and you don't look like you. Well, that's what these sensors do in response to electrical signals. That the shape of the surface distorts and changes how much light is reflected back. They shoot a laser beam at these sensors, these antennas, so to speak, and then they use a camera and microscope to wirelessly track the light, watch how the signals are changing, and then they're hoping by doing this and by capturing up to 10 hours at a time of how these antennas are how cells are communicating to one another. With up to 10 hours at a time of data, they're hoping that they can understand what the cells are saying to each other. So they have got this awesome method of capturing what electrical signals are being communicated between cells. They actually don't know yet what it means necessarily, but this is a breakthrough in that we're actually able to record these signals in really, really high definition for up to 10 hours. And they said the limitation here isn't actually the antennas, it's the imaging. So if they get better at shooting lasers at it and better at tracking it with cameras and with microscopes, they think the sky's the limit with this antenna method that they manufactured.
And real quick, I think it's worth noting on the performance side of things, like I'm going to use the analogy of TVs. Think backlit TVs where there was a light source and then each pixel was filtering the amount of light that was coming through, showing you the image. OLED TVs, every single pixel is emitting the kind of light it wants to show. That is the kind of resolution you're getting here with these sensors. Every time one of them is changing, that's because of stimuli in that specific region, which gives these researchers the kind of precision that they've been looking for. Another thing that's definitely worth noting is that because these sensors were developed for in vitro testing, they're designed in a way that you can grow cells on top of them, meaning that they can create an array of these sensors, grow the cells, and then just see how it behaves over time. So and that in itself is pretty impressive.
The potential implications of this are pretty crazy, right? Like, so that we've already, I think, covered a couple times on this podcast about nanophotonics. So the idea of using photonic computing, using light as a signal for computers as opposed to pure electrical signals. Every computer we use today, for the most part, is based on electrical signals. But this is an interesting hybrid where we have the potential to do not just photonic computing, but potentially biophotonic computing, right? So where cells are the stimulus that's causing the changes in light. It makes me think about, I think is it Cloudflare?
Yeah.
Who uses lava lamps?
The lava lamps, yeah.
As their random stimulus generator for encrypting things. I mean, you could use cells to and cell
that's
activity
an interesting thought,
to generate changes in light that are captured by a camera and use that for encryption. I don't know what the future holds here, but this is showing us that we can more closely integrate biology and the way that cells are communicating with each other and turn that into computation and computing and tracking real electrical signals in a way that computers can understand. I don't know what all the applications are. One of the things that they've alluded to, right, is being able to understand the mechanisms behind arrhythmia or to understand the mechanisms behind Alzheimer's, which both of those are very noble causes.
Absolutely.
But it's almost a little bit eerie here to say, like, we've taken one step closer to making cells and computers the same thing.
Cyborgs. That's where we're headed.
But not just not at a macro level. We're talking at the micro level, on a cellular level, which is kind of crazy.
I'm more on the the optimist, nothing bad's going to happen side on this one. I'm just excited to learn more about biology and how the underlying infrastructure of all this works, because biology was by far the worst science that I ever performed in. So if someone else is doing the heavy lifting here and that's going to unlock all the fun stuff about medicine and whatnot, I'm all for it.
No, I'm with you, man. And it's like this almost feels like the human, they always say, like, the gut microbiome is the last unexplored frontier in the human body. I don't know that I believe that. Like, this is telling me that the cells inside my brain or the cells inside my heart are communicating to each other in a way that we currently don't understand. And we know that it's electrical signals, but we haven't been able to crack the code yet. This is telling me, there is another frontier in the brain. There is another frontier in the heart. And the way that cells communicate to each other in general, that we're hopefully now going to start to be able to understand. And I hope that in biology classes, 10, 15 years from now, people are looking at this breakthrough in a textbook saying, like, this is when we started to understand the heart, or this is when we started to understand the brain truly at a cellular level, similar to the way that, like, I'm sure when you're in biology, like, we all learned about and celebrated when we first sequenced human DNA. Like, I feel like this could be like a similar breakthrough that ends up in a biology textbook and helps us to unlock a whole new level of understanding and potentially medical breakthroughs to help treat these diseases, which I think is the most important part out of all of this, in my opinion.
Dude, fingers crossed. I'm rooting for them. What do you say you wrap it up for us, though?
Yes, sir. All right. So we talked about today cells, not cell phones, but little tiny cells inside your body. They send electrical messages to one another. This is something that we actually currently don't understand, and we can't understand when we use wires. We don't have a way of sensing. But this team from MIT has made an awesome, minuscule wireless antenna that can track these messages by changing how the antennas bounce light. And similar to a funhouse mirror, a camera and a microscope are able to watch how the light reflects. And they're hoping they're able to figure out what the cells are saying, kind of crack the code and spy on cells and understand how cells are communicating to each other. And this has potential huge implications for diseases like arrhythmia and Alzheimer's, and potentially our ability to cure them.
Money. I love it.
Thanks, dude.
I think that's
the pod?
Yeah.
All right. Peace.
Later.